Hi, everybody. Welcome to the second part of our question on the failure of a ductile epoxy adhesive in the Advanced Design of Modern Aerospace Structures ABAQUS tutorial series. My name is Vishesh, and I'm going to take you through the rest of the question now. So this part of the question asks us that with the data given from the previous part, which is essentially our K1C value, we're supposed to determine the load to failure for the given configuration, a configuration that we're going to get to in the next slide, using the VCCT method in ABAQUS. Now, this is what our given configuration is. We know our material properties, we know the thickness of our adhesive, we also know our K1C value now, right? Our geometry is a little bit different in that our top cantilever beam now has a different shape. What we're supposed to do in this tutorial is to determine the load. So we're supposed to iterate over the load to determine what load causes the adhesive to fail. Essentially, at what load does the K1C of the adhesive reach this 22.2 Newton per meter square? Let's go back to ABAQUS now. Welcome back to ABAQUS again, I guess. We're going to start by creating our regular standard explicit model. Uh, Now, over here, what it's important to understand is that we've got three different shape parts, right? So we're not going to make just the one cantilever, we're going to make two different cantilevers. So let's start with the hardest part first. I'm going to save my model database as well. I'm going to call it DCB2 this time. So let's start by creating the hardest part, right? We're going to be repeating a bunch of the steps that we did in part one of this video, and it's going to be very similar to what we did there. All we need to do different here is iterate for force. But let's start, right? So what you'll find out when you go through part or the configuration that we've been given is that the cantilever length is about 5 mm shorter than the first part. So the total length of the cantilever is 285. So I'm first going to create a base cantilever that's 0.285, 0.0127. So that's my base cantilever. Now I need to create a little slope that's been given, right? So where does my slope start? For that, I'm going to choose my create lines tool. So where does my slope start? I can look at the image and I can tell you that my slope starts at, I'm going to say 50 and 0.0127. So it's 0. So 50 mm and 12.7 mm. So 0.05 and 0.0127. And I press enter and there you go. Now where does my little slope end? It seems to end at 243.6 mm and 32.75 mm. So I'm going to say 0.02436, not zero 0.04, in fact, 0.2436 and 0.03275. There you go. That's my slope. I press escape. Now I need to create another line, right? That starts at this point and it goes to 0.285 and 0.03275. And I join it to this node as well. So there you go. But you'll see that there are open sections or there are two closed sections in this part. So how do I remove this line? So for that, I click on the auto trim tool and simply ask it to trim this line. And there you go. My shape has been created. I click cross and I click done. Now, as with the previous part, I need to apply my force over here. So what I'm going to do is create a section 0.0127 and 0. And I'm gonna draw oops, done. And I'm gonna draw a line or a wire through this section, right? Add wire. There you go. That's part one. For part two, let's make the bottom cantilever. That's much easier, right? So continue 0.285 and 0.0127. Done. I want to create a section first. 0.0127 and 0. Done. And then I shall create a wire. Done. That's part two. Part three is our adhesive layer. Now our adhesive layer is also, since our cantilever has gotten 5 mm shorter, our adhesive layer is also going to get about 5 mm shorter, in fact exactly 5 mm shorter. So the length of the adhesive layer hence is going to be 0.2323, 0.0002. So that's my adhesive layer. I click done. Now as per usual, I need to define two materials. The first will be steel. I shall define the density and I shall define the elastic properties as well. My Poisson ratio will be 0.3. I'm going to enter my Young's modulus again. Okay, and I'm going to define the adhesive, of which all I know is the mechanical properties. Okay, next I define my two sections. I'm not going to have three sections because I have just two materials. So it's going to be just two sections. So, oops, I think to have called this section, I'm going to call this sphere. And I'm going to give it a breadth. And I'm going to call the other one adhesive. And I'm going to give it a breadth as well. Next, I assign my sections to my parts. So, of course, I want to assign adhesive to the thin part. And to the other two parts, I want to assign the section that's called sphere. There you go. Now we move on to assembly. We know how to do this. And this time we do not need to repeat any part, but we do need to make them independent and we do need to offset them. So I click on OK here. The first part that we need to translate by translate instance is my adhesive layer. I'm going to press done and I'm going to go out there and select the top right node of the adhesive layer and translate it to the bottom right of the large cantilever. Similarly, I shall select my other cantilever, take the top right node and translate it to the bottom right node, just so. So this is the geometry that we're going to be working with. Save. Moving on to step, we define our step as we did earlier. We toggle nonlinear geometry on and I create another field output because I need my NRR, ENRRT value, failure fracture. And I move on to interaction, which is the important step here. So as with the last simulation, I'm going to isolate my adhesive layer first. I have Shift pressed down and I am going to select Remove Selected. I go to Tools and Set Manager and create my first set, which is ADH Top, which is the top two nodes of the adhesive layer, and done. Next, I create ADH Bottom, which are the bottom two nodes of the adhesive layer. Dismissed. Next, I create my four surfaces. The first is adhesive top, which is the top edge of the adhesive. Then is adhesive bottom, which is the bottom edge of the adhesive. Now I want my cantilevers to come back, so I click on Replace All. My next surface is the bottom surface of the top cantilever, so I'm just going to call it top cantilever. Select its bottom surface, and I'm going to call the other one the bottom cantilever and select its top surface. There you go. All my geometry definitions are done. I dismiss this and I create my VCCT criterion. Now for this, my fracture criterion, I know my mode 1 this time. It's 22.2. My mode 2 and mode 3 are not directions in which my adhesive is going to fail, so I can literally give it any value. I'm going to give it a realistic value, but it's not going to matter. I'm going to press OK. Next, I need to create my two interactions. So first I create my top interaction, surface to surface, select my top cantilever as my main surface, click on surface here, and select my top adhesive top as my secondary surface. Again, my bonding is limited to the secondary nodes called ADH top. My sliding formulation is small sliding, and my property is VCCT criterion. I press OK. I do the exact same thing for my bottom interaction as well. Press continue. Bottom cantilever is my main surface, and bottom adhesive is my secondary surface. It is limited to ADH bottom with small sliding and my contact interaction property intact. I press OK. Next, I define my two tracks. I go to Special Track Manager, create track 1, debond using VCCT. My initiation step is the only one I have, and my first contact pair is my top contact pair, and my second contact pair is my bottom contact pair. It's nice. Next, I want to define loads. Before that, I'm going to define my boundary condition, of course. I'm going to press continue here and dismiss this because I want to select my boundary condition manually, my boundary edges manually. I have shift pressed down and I have selected 4 edges over here, and I press down and I encaster these edges. Next, I want to define my load. Since we don't know what our ideal load is, I'm gonna select a random but lower load for this. Let's go with 1300 and 1300 for the lower node as well. Now we need to mesh. This is going to be an irregular mesh because of the slope, but we're going to try and make it as trustworthy, say, as possible. We seed part instance, select our instances, press down and 0.001 as with the previous case. Press OK. Ask it to mesh all three instances, and there you go. As expected, my mesh is irregular. I also want to change my element type to CPS4i and press OK. All right, then. The only step that's left is submitting the job now. I'm going to create a job. I'm going to call this one job 2, press continue and OK and submit. The job has been submitted. It should not take an immense amount of time to complete. What it's important to remember for this analysis is that um, we need to iterate over the force. So the force that I have entered at this point in time might not be the correct force. We might get a K1C value or an ENRRT value that is significantly higher than the fracture criterion that we've entered, or significantly lower. If it's lower, we increase our force. If it's higher, we want to decrease our force, because the question has asked us to find the force at which the interaction or my adhesive layer fails. Uh, and that's what we're going to try and do right now. We're going to look at the monitor. Well, there you go. We have just converged. I'm going to dismiss this. My analysis is complete. I go to results and look straight for my ENRRT value, which is just 12. At least for the lower discount. And for the upper layer, we're at 21.8. So we got really, really close. So with 1300 Newton force, we've reached 21.8. What you're gonna do next is find out what an increase in the force does to my ENRRT value and what value takes me to 22.2. Spoiler alert, it's not going to be too much higher than 1300. But what is that value? Looking forward to your answers.